Yeah, Randy, for inviting us along for this ride. It's always a pleasure to participate with you and your presentations here. I've gotten a lot out of the previous two presentations, so it's been a good day. So
Today it seems to be all about bushings,
well,
right?
I'll touch on it as well. So
If 40% of all failures are from bushings, then
yeah, yep. Okay,
all
so
right.
we'll talk about monitoring and diagnostics. And when I say monitoring, it's from the point of view of continuous online monitoring of transformers and their components. And I'll start by asking all the question I always start out with dealing with users or owners of transformers is why? Why do you want to do this? And I think it's a worthy question to ask because it gets people thinking the why and the what. So we'll go through looking at some of the key components that go to make up the transformer because all these components are meant to work together as a system. And that's how we have to look at a transformer. The other way I look at a transformer, to be honest, is that as it's been hammered into my mind over all these years, it is a chemical reactor. And that's how we need to look at a transformer because after all, it's oil and paper. You have organic materials inside the tank and the bushings, and you have an energy source. So when you have all those things coming together, it's a reactor. And I'll get to the point about alarms, as I said before, be prepared. So it comes with what I've dreamed up at one point here is to begin with the 5 W's. And one needs to think about this and answer these 5 questions before writing any specifications. And they are similar. I'll go through each one of these. We go, why are you doing this in the first place? With the understanding who is going to be impacted by the plans that you wish to have answering the question why. What are you going to monitor? And where? And when? So these are important questions that need to be considered at the beginning before you, as I said, before you start writing specifications. So why monitor? And some of these notes here come from a presentation I attended some years ago now with TechCon Australia, Sydney, and this was put on by this was a contribution by FM Global in Australia. And the reasons can be as simple as reducing the risk of unexpected failures. That's number one. Even though the failure rate is generally low, well, I think we can all acknowledge that. The overall global failure rate is around 1 or 1.5% per year. It's the risk. And that's where we get into the calculations of risk is the consequence of something happening, multiply, in other words, impact financially or safety or whatever it is, multiply by the probability. Increased reliability, and that's what we're talking about, avoids forced outages with condition-based maintenance, which where monitoring can help lend a hand. So the numbers here come from FM Global. They insure facilities that include about 100,000 transformers worldwide. They do not insure specifically a transformer in a specific location. They look at it as a whole at a generating station where they're involved in, at the time, 1,300 odd generating stations globally. Their opinion is based on the losses they've seen, that the majority of the losses that they pay out on are preventable. And over the past 10 years, and this goes back to 2018, they've paid out $937 million in gross losses. In that were 554 transformer failures over the last 10 years, dating back from 2018. Excuse me. Bushings accounted for 8% of those total failures. So in other words, 45. But it represents 12% of the value of all failures. In other words, $112 million were contributed because were paid out cash money because of bushing failures. That's what we mean by the impact of a component, in this case, a bushing, has to the failure rate. Next, we need to think about who can be impacted by this. And we divide this up, and this comes from the Seagrey technical brochure, the technical brochure number 630. And this is the monitoring guide published by C. Gray. I was part of this working group, and I was a co-editor on this working group. And the time frame, we look at the immediate or short term. Who's going to benefit from this? The primary people are going to be the system operator in terms of emergency operations or emergency maintenance. And the required income they're looking for is the status required to number one, safety, continuity, and reliability of the equipment. You look at the medium term, and that's for maintenance and planning. In other words, the monitor is there to let you know when things begin to go wrong. Give you hopefully give you the time frame necessary to plan maintenance and carry it out, or maybe apply intensive care and provide that early warning. The status is the maintenance needs and when can help understand short-term replacement. The longer term is for the strategic asset management to look at replacement strategies, looking at the longer term viewpoint. And it's about the degradation, evolution, the maintenance optimization, and planning for long-term replacement needs. So talking about monitoring versus diagnostics. And this is information that comes out of another C. Gray guide, number 227, Life Management Techniques for Power Transformers. And this was published some time ago, but it applies today. Monitoring on whether it's online or offline is there to answer one question. Is the unit behaving normally? Yes or no? 90% of the time, it is. And that's the case, we'll do nothing, just carry on. Yeah, 10% of the time, the answer is no. There's some anomaly that's present. And this is where diagnostics comes in to answer the question, is it serious? Yes or no? When we say no, it means it's something that is going wrong that can be either be fixed on site, perhaps taking an outage to do some fixing on site, like a bushing replacement or tap changer maintenance, things of that nature, and then carry on back to the monitoring. 2% of the time, it is major. And when we say maintenance and repair, that when we say do something else, it usually implies removing the asset from the site, sending it back to a repair center, a factory, or calling in the scrap people to come in and carry it away. So when we look at monitoring, it's a broadband approach that's can be applied routinely. Diagnostics comes into play where you're focusing a technique and apply it as required. Drew pointed out some of the diagnostic testing that can happen. Once a monitor says, I think something's wrong, the next step is schedule, how serious is it? And then schedule the time to go out and apply the appropriate testing to it to confirm that the monitor has detected a problem and needs to be fixed. And of course, maintenance and repair, that speaks for itself. It's got to go away from the site to be fixed or otherwise disposed of. So what's the most important part of a transformer? And the unit consists of many subsystems. This comes out of that same C. Gray brochure. There are 5 major subsystems, as you can see here. And most people believe that the overall condition of a transformer is only as good as its worst performing subsystem and or component. In other words, you have a transformer. If the tap changer is showing some signs of not good behavior, as I call it, that transformer can be classified as suspect, the whole unit. If one bushing out of the 12 or however many are on the transformer has a problem, it's classified as unreliable or suspect unreliable. So the unit's condition is only as good as its worst performing component. It's something to bear in mind. So what to monitor on a transformer? And here's this temperatures is common to all types, regardless of its application, whether it's a generator, step-up transformer, a shunt reactor, a arc furnace transformer, whatever it may be, these things apply. So measurement of the top oil and bottom oil temperature of the transformer. Measurement or recording of the winding hottest spot temperature on units, my opinion, greater than 2.5 MVA. The ambient temperature is needed as a validity or reality check, I should say, on those two measures above, and can serve as a proxy for the bottom oil temperature. If you have no sensor, the theory is the bottom oil temperature of the transformer can be no lower than the ambient temperature that it's operating in. So why? Because temperatures affect everything. If it's too high, the impact is degradation of the oil, and in solid insulation if it's left unchecked. The winding insulation, the paper, is very sensitive to temperature and moisture, as Drew was pointing out earlier. And the input to many of the models, calculations that we do, temperature provides a deeper understanding of the transformer operation and behavior. And I use the word behavior quite often. And here's an example. Many of you recognize that gauge, the winding temperature simulator. It isn't designed back from the 1940s, which is what we've been using and still use today. It is a simulator. It doesn't measure directly. What it does is that, and you can see the cutaway there of the what it looks like installed on the transformer. You have a dry well and a tube that goes inside. The bulb is basically a bulb to control the expansion and contraction of a fluid that drives the indicator needle in there. So once this is properly calibrated at the factory, before the transformer leaves the factory, it's a simulation of the winding, hottest spot winding temperature in the transformer. That's what it's meant to do. However, is it reliable? Is it accurate? And in this case, this transformer here on the left-hand side there, and this was on service for about 3 months, where the winding temperature indicator was reading 50 degrees C, and the oil temperature was reading 65. This is physically impossible to happen. It means that the winding temperature indicator, the one on the left, was not properly calibrated in the factory before it was shipped. Therefore, when I'm out in the substation and I'm approaching a transformer, this is one of the first two things I look for in a transformer. First thing is I look for leaks or seeps. Secondly, I look at these gauges to see where they sit, how far they've gone in terms of that drag hand. And if it's showing that one, the winding temperature indicator, oil temperature is reading greater than the winding temperature, I point it out and say, hey, this is not calibrated correctly. Here's an example of what happens if looking at it. Now you can tell that these gauges have been in service for quite some time. This was from a published paper from a utility in the States on a distribution substation transformer. And it's the winding temperature drag hand is approximately 65 degrees C. That's the red arrow. While the top oil temperature drag hand on the left is at 110. Stage 1 fans were set to come on at 75 degrees C, and they were controlled by the winding temperature indicator. It never got there to turn on the fans on this transformer. The result, and also people going around and writing things down in the substation, people go around once a month, begin to write numbers down on their forms, goes back to the office, and it's duly entered into a record of some kind. And on that particular transformer, we can see that that problem was there for quite some time. The top oil temperature, you can see for 4 months in a row, was reading far more than the hotspot temperature. So it's an indication that there's something seriously wrong with the winding temperature indicator, but the person writing the numbers down was not aware of the relationship between the two. The person entering the data wasn't aware. The engineer who signed off on this should have been aware, but made no correction. The result is this. Now, winding temperature indicator had seized up. Moisture had gotten inside, and it stopped working. That controlled the cooling system. So when it got hot, as the top oil temperature was well over 100 degrees C, there was no control, no alarms, because the alarms were tied to the winding temperature indicator, not the top oil temperature indicator. And the fault was down, way down below. I know it was a phase-to-phase fault inside those two leads inside that tube running across those phases. So the result was, as you can see, led to about 20,000 liters of oil spread across the substation surface and below. Fortunately, no fire, but this is what happens when it's something as simple as those gauges stop working. So how to overcome this is two ways. Another example before I carry on. This is from monitoring now. An online monitor was put on the smaller size transformer. You see maximum 10.5 MVA. And this is in a winter peaking area. You can see January in 2010. They received an alarm and the output was alarms were connected into SCADA. So the alarm came in and the winding hotspot temperature was exceeding 140 degrees C. Top oil temperature at the time was 74. And this is in January in a mountainous area. So calls made out to the people to go check it out. After they got through the snow at the fence, they discovered that that unit had only one cooling fan on there and not the required minimum of 3 cooling fans. So they found 4 more fans and installed them. And the following day, the field were happy to report that they checked the temperatures on SCADA and fans definitely made a difference. The question is, before monitoring was applied to this transformer, that this situation was happening all the time. So how much aging, accelerated aging has happened on that transformer is a guess right now. But the point is that only online monitoring pointed them to this problem. And it all goes back to when the unit was commissioned in the first place, or installed and commissioned. Should have had 3 fans. Somebody only put 1. And this is what the end result was. So it's important to have cooling control, and it's there to maintain the temperatures to the maximum allowed by the standards or by design. You have it verified automatically that it's properly functioning. You can periodically turn on the cooling on or off, and I'll show you how. So whether it's as you see on the left-hand side, water-cooled or rectifier transformer in this case, or air-cooled ONA and ONF, those gauges control the cooling system on those transformers. So within a monitor, and that's what I'm talking about here, an online monitor, we have inputs from top oil temperature sensors. We're measuring the currents of high voltage and low voltage winding. And the cooling stage status, is it on or off through the breakers, the contactors on there. And we have the fixed parameters from the transformer test reports. Feed that into the monitor and it calculates what the top oil temperature should be. It calculates the winding hotspot temperature. It calculates the aging rate of the transformer and can control the on and off of the cooling system. And will also detect when the cooling fans and or pumps stop. So the output is control of the cooling system on and off, and cooling bank information and display and trending. The unit, and so it's an electronic temperature monitor. And you see the one on the left, that is it's produced by Dynamic Ratings. It is in a cast aluminum enclosure, NEMA 6X, NEMA 6P, I should say. And you can see on the right-hand side, the traditional one, and you can see there's moisture on the inside of the glass. That's an indication that moisture is inside, and it's only a matter of time before it begins to corrode the inside of that, and it will eventually seize up. So this temperature monitor is the ability to replace up to 4 of those devices on a transformer. So on the right-hand side, you can see one is for top oil temperature, one monitor. The traditional one's for top oil temperature. The other 2 are for winding hotspot temperature on the high voltage and low voltage winding. All of that can be accommodated by functionality in one electronic temperature monitor that, once commissioned properly and installed, you never have to go back and verify its calibration. With these winding temperature indicators, the vintage types, as I call them, the manuals, when you read them, indicate that the calibration needs to be verified once every 4 or 5 years. It's a maintenance task. When I inform that to people in the substations now, they're completely unaware. Most of them, I should say, most are completely unaware that that's a task that they need to do. The person who had the job before them is retired or by attrition moved away. That knowledge was not shared or passed on. So looking at traditional way of looking at it, you see top oil on the left-hand side with the traditional coolant, the traditional indicators showing how much the top oil temperature varies with the conventional ones according to, and here you're looking at load, the red line, the blue line is the ambient temperature, and down below is the status of the coolers, on or off. And that's we can take those in and verify when they're on or off. With an intelligent monitor, the control of the top oil temperature is far more consistent. It's within 5 degrees rather than variations of 15 degrees C using the traditional methods. So it reduces the rate of oil and paper aging. There's less maintenance of the oil implied and also less maintenance of a silica gel breather if there's one, if it's a free breathing type transformer. That's the biggest advantage. And since it is a microprocessor based, it can communicate this information back through SCADA to the control center, along with any alarms that may come about in the functioning of the transformer. Now, we'll touch on bushings. Drew, I thought, did an excellent job on describing the condition of bushings. And here it is, I hate to repeat things, but secondly, it's the second leading cause of failures of transformers after on-load tap changes. And that's according to some recent surveys of failures of transformers done by C-grade working groups. 50% of the time in a bushing failure leads to fires and the complete loss of the transformer. And that's a global statistic, again, coming from the C-grade statistics. Offline testing, as Drew was mentioning, I've heard people say, yes, we do it once every 3 years, maybe 5 years, maybe 8 years, or whenever they can manage somebody to take an outage to go and test these transformers. In other words, it's not always consistent doing the offline testing. But over time, the failure modes of these types of bushings is well understood for OIP, or the oil impregnated type, while RIP type bushings, they have a very different mode of failure, and I'll share that with you. Regardless of the type of bushing monitors allow you to move from a time-based maintenance scheme and testing to a condition-based maintenance regime. So the sensor, is an example of the sensor from Dynamic Ratings, is installed on that bushing test tap that Drew was explaining to you before. That is an IEEE standard, and on IEEE type transformers and bushings, that's dimensions of that tap are standardized. So at least we have that, regardless of who made the bushing to the IEEE standard, the sensor will be able to attach. It measures the C1 leakage current is what it's measuring. And same time, it has the ability to detect partial discharge measurements in that electrical circuit, because now this is in the electrical circuit. And the ability to electrically detect partial discharge is there. So one sensor doing 2 jobs. And if the bushings are made outside or in other parts of the world to IEC, at this point in time, there's about 55 different tap adapters because in the rest of the world, the bushing manufacturer decides what dimensions the bushing tap makes. If it's built to IEEE standards, it's standardized. And it has to be a good sensor protection. It has to be robust and watertight so that there's no danger of having an open circuit when this is properly installed. So how it works, you have 3 bushings, 3 phases, measuring the leakage current into the monitor, a balancing unit, we call it balancing, and the summation, because what we're looking at is the change in the vector sum of the leakage currents. Every bushing will have a different leakage current, close to each other, but still difference. We balance it out, sum it, and we view it then as a null meter, so to speak, and we look at the variation of the leakage currents phase by phase. So here's an example. This one, 69 kV with OIP bushings. This particular transformer at the time had older OIP with no replacements in stock at this utility. And in the fall of 2010, this is the view of the software. Look, and every little blue dot you see on that upper diagram polar plot represents a measurement in time of the sum currents. And the yellow ring and the red ring are the alarm limits in terms of the deviation from null that the measurements are taking place. And the location of it in the green space there is indicating, is it a power factor issue or is it a capacitance issue? So you get two measurements, a relative capacitance and a relative power factor measurements. The other thing that goes into this is the influence of temperature on power factor, or the influence of temperature on the leakage current. The graph down below, you see the red trend and the blue trend. We take a top oil temperature measurement. Remember I said top oil temperature is vital for every transformer. That is an input into this monitor. And you can see here that as that top oil temperature increases and decreases, that's the red line, the blue line, which is the sum current of the three bushings, increases as well. But when the top oil temperature goes down, it decreases. So that's one of these things that's in phase with temperature, the increase and decrease of the leakage current. This points to a power factor problem because we all understand power factor, temperature influences power factor measurement. So this is how we pick up. The monitor is looking for this sort of situation and will raise a flag that something's wrong. Come and pay attention to me, but something's going wrong with these bushings. It looks like a power factor issue. And you schedule the outage, go to and test it. And yes, indeed, they tested it 2.13% power factor. And in this one, bushing, center phase, there was also PD activity. And we can pick up that PD activity by looking at the charts here. Every point represents PD activity going on inside that bushing. Inside the bushing, not in the transformer. So this is a method of doing two jobs: is detecting the changes in the insulation of the bushings, but also if there's a partial discharge inside the bushing and or in the transformer. I've run into a case just yesterday where somebody said they had questions about, I don't see any oil in the top of my bushing. And this is actually more common than one thinks. But here, this was on a 138 kV distribution substation transformer. And the monitor from Dynamic Ratings found this, detected this. The monitor had been in place for 2 years. And one day, the little graph you see down below there is a graph. The green line represents the sum of the capacitance value. So it's the measurement of leakage current is directly proportional to the capacitance value. And there, and the light blue line is the sum current going up. So the vector sum current is increasing. So within 24 hours, on this particular day, the condition of the bushing went from normal, I'll call it, to abnormal inside 24 hours. They called up and they said, well, they had never seen this sort of thing before. So what's going on? And our experts looked at it and said, we suggest you send somebody out to the site and look for signs of an oil leak. When the engineer got there, they discovered, as you see in the picture, no oil in the sight glass, but they did see oil leaked out from the bushing and down the side of the transformer, excuse me, on the left-hand side. So, and it was apparent that somebody had put some blue goop. I don't know what the heck that is, but that's where it was leaking from, the interface between the porcelain and the flange itself. So the monitor did point out that this change in capacitance was the decrease in capacitance was due to oil leaking out, and please send somebody out because if they let that continue, there was a big risk of that transformer failing in a not very nice way. So this is the benefit of monitoring. It may not be apparent the first time you put it on, but in service, it picks up when the things begin to go wrong. Drew was explaining before about the failure modes, and we picked this up as well with monitoring. This is the only way we could pick this up. On the left-hand side is the OIP typical failure mode, as I was explaining before, as temperature changes, we see leakage current change on the bushing, so due to power factor changes. And that's what that graph shows on the left-hand side, is an OIP bushing on its way to failure. The graph on the right-hand side is the leakage current measurements from 3 RIP bushings, resin impregnated paper bushings, and to 230 kV. So the yellow line represents the the leakage current from bushing on phase 3, H3. The blue line across the bottom represents the sum current. So it's essentially around 0. So the sum current is still null, except for some point in time in May, I'll call it May 7th. For whatever reason, you can see a very sharp increase in the leakage current. And that increase was an increase of capacitance of 85% in 1 hour. So something happened inside, and it was a shorting. It started, these things in RIP bushings usually start with a small void left over from the manufacturing process. And that void is impacted by full voltage on the transformer, of course. And over time, it begins to eat away at the resin and begins to eat its way to the next layer of foil, next layer, and it just eats its way through. And what you see here is increasing leakage current, which represents an increasing capacitance change, 85% in 1 hour. That's the difference in the failure modes between OIP type bushings and RIP bushings. So the RIP bushing here failed. Now, the good news is it did not explode. That's the good news in all of this. Still, nothing is infallible in our world, in the electrical world particularly. People who say, yes, this thing will never fail, I think are telling a big story out of school. The failure rate is, we don't know the exact, we cannot compare, I should say, failure rates of RIP to OIP, because the population out in the field is still largely OIP type bushings. RIP bushings are a smaller percentage of the installed base around the world. But the point is, this is, by monitoring it, you know when things begin to go wrong. Time to react on an RIP failure is not as great as you get on an OIP bushing, unfortunately, but that's the rules. Those are the rules. The other thing on RIP is at an IEEE meeting a few years ago, the bushing expert with ABB in their factory in Tennessee gave us all a very nice talk on application of RIP bushings. And the one thing he kept in reinforcing, and it just sticks in my mind, he said, if the bushing, RIP bushing says maximum rated current, for example, is 800 amps, it is 800 amps. It's not 801 or 802, it is 800 amps. Remember that. So when you're looking at overloading a transformer and you're using RIP bushings, make certain you understand the current rating of these bushings and the amount of overload you want to put on them. Otherwise, you'll see something like this happen, where the resin will melt at a higher temperature. And Drew alluded to that. It will melt, and what you see here is a crack around the top and the resin coming out. Never overload an RIP bushing. This is what's going to happen. That was the words from directly from the ABB chap. We talk about tap changers, and I found that I have been familiar with that vibroacoustic technology for some time. So again, this is the only mechanical moving piece that we see on a transformer other than a fan motor or a pump motor. But it's still quite important to understand that this is functioning properly. One thing that has been noticed in some of the failure statistics from Seagray is that tap changes have been known to fail shortly after maintenance has been carried out. So that's why testing, as was mentioned before, the vibroacoustic, is a good idea to test it after it's been maintained to make certain you didn't introduce another problem into the repair. One of the easier ways, I'll say, about, and this is proven over many years now, about externally with compartment type tap changers, as you see here, is effective about is the temperature differential model between on transformers equipped with such a tap changer. And so the oil in there is separate from the main oil in the tank of the transformer itself. We have the motor operator down below, and essentially it's a model that basically looking for problems of coking contacts inside that tap changer compartment. What that does is that the coking, the misplaced or excessive wear in the contacts or misalignment of contacts increases the temperature on the contacts, that increases the oil temperature, increases the coke building up of coke on those contacts. And basically the oil temperature in that compartment begins to overheat and overheats greater than the tank temperature. So it's a simple model. You measure the temperature on both the tap changer, and you can see magnetically how temperature sensor and another one on the main tank. And you do make a calculation inside the monitor. It compares the two temperatures, it measures the two temperatures, and then computes a temperature difference over a rolling 24-hour period of time. So it's a weighted temperature difference. And once the tap changer temperature, compartment temperature begins to increase and is about 10 degrees C higher than the main tank, the alarm goes and say, hey, got a problem with this tap changer. The oil is overheating, take an outage and schedule maintenance to find out what is going on. And this is what some people have found inside. And what you see on the left-hand side is a picture of a worn, excessively worn stationary contact. And you can see the wear and tear, the wear on it, the poor contact area. We all know what a bad electrical contact leads to, overheating, and the coking, which is all that black stuff you see on the contacts, is what you get. More and more of that you get, the more and more overheated it comes until potentially it can go burn its way open and you have an open circuit, which is really bad news for the transformer. So on the right-hand side is what that stationary contact should look like. Is in good unit, no excessive wear, and no coking is present on that contact. That's what happens inside the on-node tap changer when things begin to wear excessively. The other thing to count, the ability to count, I should say, is the number of operations at each tap position. Again, from the monitor. So here we see a range of tap positions between 1 and 12. And what you're seeing here up the left-hand side is the number of counts, the number of times that the switch has moved through that position. So it tells you on the chart how many total times, how many taps today. The alarm, maximum taps per day, you set alarm on it at 130. And at the moment, it says alarm status is on, or it's available to be on. So it's an indication to tell you which taps are getting, as I call it, seeing the most activity, the most wear, but also in case that something goes wrong and begin to see a higher number of tap operations per day, that's usually an indication of something going wrong with a setting on the relay to control the tap changer or some input that somebody has fiddled with. Now, dissolved gas, this is a broadband approach for the active part, the core and coil. And I think we all know that dissolved gas and oil is a way to, because it is in contact with the component in the active part. If faults occur, that the oil will begin to degrade, gases are generated, and any sudden increase in dissolved gas is the best indicator of something going on inside the main tank itself. So I'm not going to go into this. We could spend all day talking about DGA and interpretation, but here's the impact. The strategy adopted by some major utilities, let me say, is to deploy across a population of transformers, either a single or two gas DGA monitor on every transformer. And I stress a selected population. 90% of the time, you're going to find that the unit's transformers are behaving normally. Back to that one of the very first slides. 10% of the time, some anomaly appears and an alarm is initiated, and that's when the process has to start to go and take an oil sample to be analyzed, together with other testing, like what's the temperature in the gauges, what's the loading on the transformer, how's the weather today, is it hot, is it stormy, is it minus 20, or is it plus 40? Those things. All of that information helps decide on a course of action. One of the things to do is to turn the unit on in service of close surveillance, perhaps temporarily installing a multi-gas monitor to observe behavior, gassing behavior of the unit in operations, along with things like loading of the transformer and the ambient conditions. What you're looking for, and this is from C57104, the latest guide, is and this chart, in case you're trying to figure this one out, this represents, across the bottom, temperature in the area of the fault, not the top oil temperature, not the ambient temperature, the temperature of the fault. And you can see it at the lower level of less than 100 degrees C. Sometimes you'll see cold plasma, catalytic type faults, partial discharge, for instance, where hydrogen is the main gas generated. But as temperature increases in the thermal fault, because it is a thermal fault of some kind, the generation of hydrogen drops off to be picked up by methane, by ethane, by ethylene. And as temperature gets higher, you get into discharges above 1,000 degrees C. You begin to see hydrogen being generated again together with acetylene. That's how to read this chart. So it's not an interpretation chart. It's a chart to give you some clue about the rates of generation of these different gases. And this is a very simple example from a gas monitor, a single gas monitor on a brand new transformer some years ago, where it was put in service. And this is what we'd expect to see: some slow increase over the first period of time of transformer being energized, but all of a sudden something happened, or some fault presented itself, as I call it, and the gassing increases dramatically. In this case, there was no waiting around. This is abnormal to the highest degree. Take an outage, take the sample, find out what's going on. In this case, it was core insulation that was not properly installed inside the transformer was causing this fault. I talked about maintenance, and one customer actually, tell me, well, if I do maintenance, how can I justify this? One of them is perhaps reducing the maintenance cycles. And when you look at the maintenance task on the left-hand side, you can see winding and oil temperature indicators I was talking about before. If the monitor, you don't need to go out monthly and write all the numbers down. You can have it digitally. It's thermal monitoring of the transformer. There's no need to check, as monitor is continuously monitored and has a greater reliability than those older mechanical gauges on the side of the tank. Cooler system and inspection used to be yearly, perhaps. Now it's condition-based, because the ETM can look at and monitor the cooling control, and also any components begin to go, any fan motors start to fail can be detected by watching the motor current drawn by the fans and or pumps. DGA could be 6-month frequency, could be 12 months. Minimum recommended is annually. So monitoring technique is with an online key gas, 1 or 2 gas plus moisture on the transformer. Provides for continuous monitoring of hydrogen, moisture, and partial discharge. In other words, looking at the gases produced by partial discharge. And oil quality, there's nothing available to measure things like color of oil or IFT of the oil or dissipation factor on the oil. The point is that when gases begin to become generating, it's time to do something. In the OLTC, you can look at oil quality from the point of view, you can monitor for gases on those separate compartments on the outside, same as a transformer. But you also have the advantage of noting the tap count and the I squared T, in other words, current interrupted during a tap change, and the temperature differential. And with those things to alarm you, that's the time to go while you're out there checking things out, take the sample for oil quality on the tap changer. Bushing tests, I think we've beat that one to death right now. Periodic LTC inspection, normally 5 years, but if with monitoring, as the vibroacoustic was showing there, on condition, or as the OEM specifies. Electrical testing, again, you're looking for indicators when something begins to go wrong, like dissolved gas analysis telling you something's going wrong. And the visual and thermal inspections, yearly or none or on condition, but also some utilities have put in stationary visual and thermal cameras in their substations to periodically scan for security reasons, but also inside those cameras, there's thermal images where they can scan the substation, look for bad connections on bus work and on the transformer itself. So these are some of the things that can happen. And alarms. I think Drew alluded to it, I alluded to it. Asset monitoring is not set it and forget it activity. Don't think of it that way. Responding to a warning too slowly or ignoring an alarm altogether, and I've seen examples of both, can turn a simple maintenance issue into a significantly more expensive problem. An alert that goes unheeded is not a technology problem, but rather an issue of execution, of reaction to the monitor. Therefore, it's critical to formulate a response plan when monitoring technology is being installed. Having monitoring technology in place is the correct first step. Second one, train people. Train for everybody, that identification of who, train everybody that will be involved in this. Have them understand what monitoring is, what it's going to do for them, and pay attention to alarms when they come. It's critical. It's to ensure that your team of engineers and technicians know what to do when alarms go off. Ignoring it or them. And I've seen cases where, an alarm goes off on a gas monitor and somebody in the control room looks at the light on their panel and wonder, what the hell is that? Pushes the reset button. Half an hour later, something goes up in flames in the substation. Nobody trained that person what that new light, alarm light on the annunciator was all about. That's what I mean. So alarm response, and I give a very simple example here. Right now, most people have an alarm response plan for existing alarms you get, like top oil temperature alarm, or tripping on a protective relay. There's procedure in place. With monitoring, you add to that list, and these are just two simple examples. You have a top oil temperature alarm and loading. It's gone above the nominal rating of the transformer. The diagnostic is the transformer oil is currently operating at a temperature higher than the first level of alarm. And generally speaking, you have 2 levels of alarm. It's apparently caused by the high load currently applied. That's the diagnostic. Prognostic. What's going to happen if you choose to ignore this? If this condition is maintained for several weeks, it could result in accelerated oil aging. That's the prognostic if you just leave it. Recommendations are go out. Is the cooling system fully operational? Yes or no? Is it a really hot day and that's why the oil temperature is high? Evaluate the acceptable load with regard to the ambient condition. Consider reducing the load on the transformer if possible. This is very simplistic, but the point is all of these monitors employed are going to present you with alarms that you've never seen before. Plan ahead and plan action response plan similar to what you see here. Without it, you're losing all the benefit of the monitoring. So a recap. Online monitoring is becoming commonplace and many utilities are beginning to realize the benefits of these technologies over the out-of-date and aged equivalents. It's a valuable tool for condition assessment. It allows utilities to perform predictive asset analysis for replacement, determine the optimal operating condition-based maintenance regimes, manage their performance with that increased reliability and safety of the network. And it's the value of the data. The acquisition of this data is important for knowledge of real-time operating conditions. Processing of the data to acquire information and knowledge is what makes the data valuable. So the next step in all of this, from my perspective, is people start talking about AI and some of the other knowledge-based systems, anomaly detection. In order to have that and make it work, you need data, you need valid data to make it work. So that's the other important. You're collecting the operating condition of the transformer all the time from the transformer. You're just not going out once a month and taking a snapshot, so to speak, of the condition. You have the history of operation of the transformer when you have all this data. Capture it, make use of it, and it also makes for a great learning tool for new engineers and technicians coming in to have them understand why monitoring is there and review with them alarms and issues that you may have caught had monitoring not been on that transformer. So thanks for your time. Randy, I'm
Thank you very
ready
much.
for questions.
Thanks very much, Brian. First question, would you ever consider having a monitoring system take the transformer offline like a relay?
My answer to that is no. And the answer from a lot of my peers is no. In the guides, you'll find the answer is no. It's there to wave the flag, so to speak, and start your research into why you look at the data coming in. You have the data file, you have the archive of data, and you have to look at it from the point of view. If I'm sitting there and I'm the operator, I get the flag. The first thing I'm going to do, number one, is ask the question: is anybody in the substation? Yes or no? Right? Make them aware of the alarm. Number two, look at the data. If I see DGA data going from nice steady baseline, and all of a sudden you saw, like in that one slide, going like that there, and if that, I say this is really serious. If somebody's in the substation, that's advise them to leave. But at the same time, prepare to take an outage to go take an oil sample if it's really such. So that's the benefit of online monitoring, is also tells you the severity of something going wrong. And that's the point. Schedule an outage. If it's a bushing going out of control, so to speak, present the data to the system operator saying, hey, you know, that transformer, this bushing, it's going bad. And please give me an outage time. I got it within the next 24 hours, whatever. And now you're equipped, you get the outage, you get the right people, the right equipment, spare bushing if you've got it, take it with you, and the test kit, so that you're making one trip to the substation to confirm the alarm and potentially fix the alarm there. That's the benefit of this. So automatic trip, not necessarily. That's what those protection relays are there for.
Okay, thanks, Brian. Okay, let's see. Next question for you. Can you explain how your monitoring systems help teams respond to alarms more effectively? What kind of training or planning do you recommend for transformer owners to be ready?
Well, training similar to what I've just given here, but in a much
Right.
more broader scope. And a lot of it, though, depends on coaching them through why are you doing this in the first place? And that's always the first step, in my opinion, Randy, is
Mm-hmm.
identify with them, okay, why are you doing this? Who's asking you to do it, number one? Is it the big boss up top? Is it the asset manager? Why is he asking? There are some utilities in the world that monitoring transformers, they have one purpose only, and that is to answer questions to the regulator in their area. So some utilities, and working with your regulator, have designed monitoring systems to monitor only the active part of the transformer. And that's from the point of view of, because the regulator is only going to give them money to replace a bad asset. And the active part, meaning that's the most prevalent, serious failure thing one with the serious consequences. If it's a bad bushing, that's optional for the utility to do it. That comes out of the utility's pocket, not from the pocket that the regulator approves the funding for. So that's what I mean by you have to answer the question. Or is it a particular family of bushings that you have a problem with? Is it particular brand of tap changer? So, and that's what you lead the conversation through. That's what I usually start with, is starts a conversation.
In your experience, what's the biggest misconception utilities have when it comes to transformer health monitoring, especially with older transformers?
They assume that if I put a monitor on this transformer for 6 months, I'll understand how it works. But then I'm going to go move that whole monitoring system to another transformer and leave it there for 6 months. And I say, wait a minute, you've already tried it out on one. If you move it from that one to another one, you're going to get hopefully the same data. Not exactly the same data, but the same performance out of it. What happens with the one you've just moved it from? What happens if it begins to have a problem? You've just lost your insurance on that one, right? It's like car insurance. I mean, you have to look at this as an insurance. And that's why that insurance company looks at it from the point of view, a lot of the money they paid out for failures were preventable. And they say that monitoring, they'll never give a rebate for monitoring or reduce the premium, but they look on it, Randy, as a little bit more insurance from their point of view that the owner of the asset is doing the right thing to minimize the risk. And that's what it's all about, minimizing the risk.
You mentioned AI. There's going to be companies that are going to try to use AI to monitor their transformers.
Yes.
So they don't have to have workers do this. It's like using AI to look at mammogram results instead of a radiologist.
Yeah.
So is this going to be effective?
And I don't know enough about AI other than how to spell it, Andy. All right. I'll start with that. Okay. But I look at this and I look at transformers. I mentioned before, you have to look at it as a chemical reactor. And chemistry and physics operate according to certain rules that have been around for a long, long time. And we understand things like Ohm's law. Ohm's law doesn't change just because you have AI, right? It's still valid. And all the other rules of physics that apply to transformers. The thing is that where people are looking at what the example you gave of looking at mammograms is that you have a whole wealth of knowledge or history of diagnosis, right? In transformers, we don't have the same thing. Some utilities will have a set of data, but that data is applied to their fleet of transformers operating in their geography and their climate conditions, right? So just because that transformer made by brand XYZ worked well for them, it may not work well for an area where, up in Alaska it worked, but it may not work as well in southern Italy, right? It's a whole different set of circumstances. The other thing is we don't have enough data to go the route of mammogram type of history. We don't.
Right. Yeah.
And I still look at this now there are ways to take the data and look for anomalies. And I've used this myself. In other words, machine learning.
Right.
Look at a transformer as a machine and this is where you begin to look at behavior.
But Brian, won't that be included in the test equipment, in the monitoring equipment?
My experience is you need something, a higher processor computer to handle it because you need to store data.
I wonder if all the technology that's coming down the line won't include AI.
You need a big database.
Right. Okay.
To go to run it from. That's been my experience, Randy. And
Yeah.
I've done it. I've picked out problems of things that would normally miss. You would miss it on a graph. You would miss it on a trend, but it's hidden in the detail, right? Whereas, and there's lots of that software. It's on the web. You can go buy it off the web. And that's what I've done is I've used it. And every time it picks out, it's like, pardon my French here, but I'm looking to pick fly shit out of the pepper. is what that's what to me anomaly detection is all about, Randy. Sorry if I
Yeah,
offended anybody, but that's the best analogy I can put to it.
sure. Yeah, okay. Well, this is just the beginning of the next
Yes,
wave of this technology, and
I
who
agree.
knows where this is going to go. It's a revolution that's going to shape and touch everything.
I
Just like
agree.
automation, in the last
Mhm.
45 years in the
Oh,
industry, I've seen the automation take place in
yeah,
the T&D industry. And
yes.
this will be the same thing. It's just another layer of it's just
Another layer
another
of
layer of
analysis.
analysis
Yeah,
on top
yeah.
of everything. So it's a tool, right?
Yes, yeah. The
But
thing is, there's
I
still,
would remind everybody that when you look up artificial in the dictionary, the definition is deceptive, false, fake, phony, pretending.
I have never thought of it that way, but
Not authoritative. It
okay, yeah,
artificial means phony, deceptive.
yes.
Okay.
Grain of salt, in other words, right?
Yeah, yeah.
Yeah.
All right.
Machine learning is a different case, and that's where
That's
automation
right.
is. Yeah, yeah,
That's right. You're absolutely right.
yeah.
Okay, great. Good presentation. Good discussion.
Thank you.
Good to see you again.
Nice to
Thank you
see
very
you,
much
Randy,
for
as well.
participating.
And
Yeah.
Andrew and the other presenter. That was useful information for, I've learned something today. That's the good news
Yeah,
today. Yeah,
it's okay. Well, this is one of the better live online forum presentation that we've had. It's really a great team.
good. Glad to hear
Good.
that.
And I look forward
Yes.
to seeing you all soon. Thank you very much to the people who attended today. I hope you
Yes.
got the information that you were looking for, the hoping to get. Please contact Drew and Brian of Fuad later if you have other questions.
Mhm.
Their contact information is in the chat. Next week, you'll be receiving from us an email with with instructions on how to download the presentations in case you didn't get them today, and also to view the video presentations. We're recording these presentations. We'll upload them to our video library this weekend. Okay, thanks
Very
very
good.
much for everybody.
Thank you,
Okay,
Randy.
and I'll
Seeing you.
see you all soon. Okay,
All right.
thank you. The next one
Bye-bye.
is in September. The next
Oh,
so
wow.
have a good summer, everyone, and
All right.
we'll meet up again in the fall.
All right.
All right,
Bye.
thanks very much. Okay, bye.
Bye.